All right, so I'm Alan. Let's go ahead and figure out what happens when you look at the field contribution to the Lagrangian. So, if you recall, now we're just ignoring gravity for now, okay? So we have W alpha is this formula. And once you write out, sorry about the reflections, once you write out all the parts, you have the electromagnetic contribution. This is Q2 dagger minus Q2 dagger Q2 is just a shorthand for that. Commutator, the anti-commutator notation. You have this lovely formula in terms of Z. So there's a 2 and a 1 neutral current element for that. And I'm very verbose with these elements, E over H bar. And I know there's G prime and G, but I'm just writing it out explicitly. And then you have the interaction terms, so the W plus and W minus, the Q1, Q2 dagger or Q2, Q1 dagger. So these are, when operating on our Clifford algebra object, are going to have the effect of switching out of 1 and a 2. You also have the, what I'll call the neutral current contribution from SU3 on the right. So remember, U1 is split up into two parts. This is the part from the left, the Z and alpha, or A, I should say. And then the Z and A from the right is actually this, minus I over 6H prime, A alpha minus tan Z, and then the sum of those three neutral elements. So each of the neutral elements up from the right contain this one. This is just B alpha, by the way, if you look at the usual construction of these terms. So now we're interested in the field, which is just accomplished by taking the covariant derivative and basically creating a curvature. This is the curvature out. And then we can write that out in terms of all these terms. So this is just from the left side. You have F, which is our usual F. Again, only with the 2 component. Z with its usual components. W minus W plus. And then you get some cross terms in here. Blaze over this, but you can, the math gets nice and juicy once you start breaking things out. And then finally your contribution when these last sets of terms are really from this part here, from the curvature, okay? So that's why you get A and W plus and minus, Z, W plus and minus, and then W plus and minus interacting with each other. What we're really interested is in squaring this. So when you do that, and I've just written out the neutral component, so we have the square of the F component, square of the Z component, and then there's a cross term for F and Z. Now immediately you're probably looking at that going, uh-oh, because the standard model doesn't contain this. But do recall that there is another component here from the right side. So here's me writing out the whole right side of this for G alpha. There's other terms for gluons, but I'm ignoring those for now. And when I square it, I get these components from the square. So what we know is that the Lagrangian is going to be some linear combination of these two, L1, L2, lambda 1, lambda 2, I should say. And if you set lambda 1 to this, and if you set lambda 2 to this, then what happens is quite amazing. Your terms in front of both Z alpha, to the square of F and the square of Z, give you negative 1 over 4 mu 0 for both of those. And this cross term here completely cancels out. So you end up exactly with the Lagrangian one would expect from the standard model. So one of the interesting things to note of this is like a new prediction, so to speak. This term, remember all of these are running constants, right? Like theta W is not a constant. It's a term that varies based on energy level. But this lambda 2 is the part that goes in front of the gluon field. So while it gives us the correct terms for the electromagnetic field and the Z field, and we get all the correct terms, by the way, for the W plus and minus when we grind through this full calculation. This thing in front of our gluon term is going to vary at different energy levels. Okay, and it turns out, if I'm remembering correctly, that this term drops close to zero, basically, at high energy. So at high energy, the contribution to the total energy from the gluon fields here drops to zero. Asymptotic freedom is actually predicted in this constant, if I'm remembering properly. Here's another way of writing this constant you see out in front in terms of the find structure constant.